Hello, 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 hello. Mic test. Can hear, is it? But room cannot hear. Check, check, check. Room cannot hear. Is that is? Oh, this is for yours, is it? Oh, okay, okay. The thing is, the thing is, I have some notes on my slides. Oh, check, check. Oof. Okay, can you just terbalik this thing? Wow, problem, right? Okay, lor. Then I will. Yeah. I can't click though. Okay, now I can. Okay. Good evening, everyone. Hi. We are finally starting. Apologize for the delay. Uh, and it's a very rainy day, but unfortunately, the rain doesn't really affect us because we are deep indoors. So I hope you guys are as comfortable as you can be in a non-air conditioned room. All right. I'm Sharad. I am the Astro head of this year's committee, and today I'll be talking to you a little bit about space telescopes. This is today's agenda. I'm just going to very rapidly click through. We're going to talk about ground-based telescopes or terrestrial telescopes, a bit of pioneering work, the NASA Great Observatories, which includes Hubble, and current and future efforts into space telescopes. Right. Without further ado, let's move on. Right. So first of all, right, most telescopes are ground-based because that's where we are. We are on Earth. Right. The problems, however, are a lot. We start off with the atmosphere. The atmosphere is like a very big blanket covering the Earth. It is opaque to a lot of frequencies, and it's thick, it's turbulent, and it reduces the maximum resolution of, worsens the maximum resolution of telescopes. So how do I put this? Let's say your friend draws a big dot on a piece of paper and brings it very far away, right? The further he goes, the smaller the dot's going to appear, right? Everyone agree? Right? The further something is, the smaller it looks to you. Do you guys agree? Yes or no? Yes. Okay, good. The thing is that with an atmosphere, the smallest thing you can perceive is quite big. Without an atmosphere, the smallest thing you or anything else, or in this case a telescope, can perceive is a lot smaller. This is what we mean by improved resolution, right? The Earth itself poses other problems, right? It has a non-zero surface temperature. By non-zero, I mean no, not 0 Kelvin. Its temperature is 14 degrees Celsius on average, and it emits strongly in the mid-infrared. I'm going to say mid-infrared a lot in this presentation, and you guys will see why, right? And there are other reasons, right? When we're on Earth, there's obviously gravity. We need to we need to have structural reinforcement. We have earthquakes, we have dust, you have to regularly maintain, you have to clean. There's a lot of things going on, right? And obviously there's light pollution. This means you can't have your telescope where it's easily accessible right outside. You can't have your telescope in, let's say, Fort Canning Park. That makes no sense because the city is right next door. You have to go to somewhere like Tioman, or in Europe's case or in America's case, they have to put their telescopes in Hawaii or Chile to observe things without light pollution. Right, okay. Can I play this GIF? Right, so this is an image of Sirius A through a telescope. right? The reason why it's moving steadily is because the telescope is pointed in one direction. It's not tracking the star. But notice all of the jittering. That's completely due to the atmosphere. Notice that the star itself is a brilliant white, but you see all of these red, blue uh, artifacts. Right? This is exactly why stars twinkle. By the way, they're actually point sources of light. And if you look up at the sky, if something doesn't twinkle, it's because it's a disk, and that means it's a planet. Because planets are big enough and near enough that even though to our eyes it looks like a point, if you zoom in close enough, you can actually make out the circle, right? So it's just a very short demonstration. Sorry to blind you all guys, but I couldn't find the dark background of this. This is what the atmosphere absorbs. I'm not going to go into very much detail because there is a lot of detail in this. Long and short of it is that this is the visible region. The atmosphere doesn't absorb a lot of visible light, which is why we can see things, by the way. It absorbs significantly in the ultraviolet. It absorbs quite a bit in the mid-infrared and in the far infrared. Beyond the infrared, it becomes transparent to radio waves again. That's why we can radio waves and microwaves. That's why Wi-Fi works. That's why Bluetooth works. That's why we can listen to the radio because it's transparent to those frequencies. Okay, this is a comparison of some of the biggest, most impressive ground-based telescopes so far and yet to be built. I want to point out a few key examples. First of all, the Arecibo Radio Telescope. Who's seen pictures of the Arecibo Radio Telescope? Raise your hand. Anyone? Okay, if you have not seen it, feel free to Google it. It's spelled Arecibo. It's basically a gigantic hemispherical, no, not hemispherical, paraboloid thing. Okay, for simplicity's sake, it's a bowl-shaped telescope. They found a nice depression in Puerto Rico, and then they were like, okay, let's build a telescope here, a radio telescope here. The reason why it's so big is because radio waves have very long wavelengths. Can we leave the questions till afterwards, if you don't mind? Right. There will be a Q&A session, don't worry. Yes, so where was I? Yes, radio waves are on the order of 1-2 meters wavelength. And that is one of the reasons why radio telescopes need to be very huge. There's another radio telescope in China that was recently built or is being built, I can't recall, called the 500-meter aperture spherical radio telescope. So these are radio telescopes. But that's not what we are here for. We are here for the optical and the infrared scopes, which most of these are, right? We'll start off with these two telescopes. The Hooker telescope was built in 1917. It's roughly the size of the Hubble Space Telescope, if you notice. So that's about 2 meters, 2.5 meters on this scale. More recent telescopes, you notice that the more recent we get, the more bigger things are, right? In 1893 and 1900, telescopes were tiny, so you could have a mirror that's about maybe this big, that's about a meter big. Now even the space telescopes are huge now. So if you look at the Hubble Space Telescope, uh, okay, we'll get to exactly how big the Hubble Space Telescope is later. Looking at some key examples, the Very Large Telescope was a big effort by the European Southern Observatory. And there are 4 separate uh, stations which are effectively join up to that dotted circle over there. So you have 4 different mirrors, and this is a concept called interferometry. Some people might say it's not, but the idea is similar, where you have multiple different cameras or observers or sensors, and you combine them into an image that is not as big as all 4 combined, but still bigger than any one of them. Right. Some other key telescopes, the extremely large telescope is really extremely large. It is huge. This is about something like, if this is 30 meters, then this is about 35, 40 meters across. That gigantic hole in the middle is where the secondary mirrors and where all the sensors are. So if you if, okay, so we're not going to have observations today, but on another day, if you come down and if we choose to bring out what we call the C8, the C stands for Cassegrain. So what happens is light comes in from one direction, hits a mirror on this side, bounces off that mirror, hits another mirror on this side, bounces off that a second time, and goes into an eyepiece in the center of the back of the telescope. That makes for a very compact telescope, which means we can actually increase the effective focal length of the telescope, which is zoom, but still keep it physically compact because we are reflecting light one, two, three times. So your telescope can be roughly a third as long as an ordinary telescope that uses lenses, for instance. Okay, so now these are these are a bit lighter in color compared to the rest because they haven't been constructed yet. One thing in particular is you might notice that more recent telescopes use these segmented parts. Okay, excluding the Giant Magellan Telescope, most recent telescopes use segmented mirrors, and these are hexagons. Um, the reason why this is happening is to alleviate some of the issues I mentioned earlier on about earthquakes, structural rigidity, and so on. It actually makes these mirrors lighter. So imagine you had a 40-meter wide block of glass, and you had to get someone to polish that glass and coat that glass and ensure the polishing and the coating is correct. That polishing has to follow, a mathematical formula. It's there is this surface and there's a formula for it. You have to polish it down to like something like a tolerance of a few micrometers, hundreds of nanometers. Actually, no, yeah, hundreds of nanometers. So that's about the wavelength of visible light. And those are the tolerances involved in polishing modern telescopes, especially telescopes this big. And imagine you have a single mirror about 45 meters in diameter, and you polish it wrongly. So you have to throw away the entire bit of glass. Or if you, okay, forget polish. Okay, you polished it, okay, and then you coated it, and then during transport, right, you dropped it on the floor. Now it's not likely to happen, but it can happen. So this is very straightforward. They realize, okay, that is stupid. We're just going to waste a lot of money trying to polish one mirror to the specifications we need. So they were like, okay, you know what? Let's just segment it into hexagons. There are downsides to it. I'm not going to say, okay, this is a free lunch. There are downsides to segmenting mirrors like this, but the benefits drastically outweigh the downsides. Number one, you can actually control each and every one of these uh, segments individually. And since you can control them, you can use a computer to control them. And since you can use a computer to control them, you can detect if there's something going on. You can immediately inform the staff, and they can take possibly automated corrective action. Not least, you can code each of these mirrors separately. If something goes wrong in one segment, you can be like, okay, never mind. This is just one segment out of three 200. It looks like 200. And yeah, so that's one big advantage of these segmented mirrors. And notice that all of the newer telescopes, most of the newer telescopes have this, including, of course, the James-Webb Space Telescope. So if you guys were wondering, hey, why does the mirror look so strange? This is why. Okay, so let's, is there anything else I wanted to say? Yes, actually the Arecibo radio telescope also had this same concept of adjustable segments. It's just that people hadn't figured out how to do it for glass yet, right? And now they have. Right. Okay, this is a comparison, a two-scale comparison of the largest Earthbound space telescope. So as you can see, there are one, two, three, four big buildings for the very large space telescope. That's 20 meters, by the way. So look at how huge the extremely large and the 30-meter telescopes are, right? Something like 80 meters. 80 meters is, can I give a reference frame for 80 meters? Okay, probably about the size of the Singapore Flyer. So imagine a mirror, a big glass mirror, roughly about half the size of the Singapore Flyer. That's how big it is. Uh, these are slightly smaller telescopes, except of course the giant Magellan telescope, and you can I can actually see the 1, 2, 3, 4, 5, 6, 7 mirrors inside. So yeah, okay. We start off with, and now we leave the ground, we go to space. We start off with early space telescopes. These were considered as early as 1946, a year after the World War, because America was magically decided that rocket scientists were not Nazis anymore, and were like, "Yay, let's just bring them over." And most of most Apollo scientists were Nazis at some point. Um, they launched 4 of these OAOs, orbiting astronomical observatories, between 1966 and 72. Can someone tell me what else was launched in this time period? Yes, thank you. Right? Apollo 11 was launched in 69. Apollo 30, 17, the last one was launched, I think, in 72. So yes, roughly the same time period. So that's clearly when, space exploration really started to take off. Uh, Unfortunately, not all of these telescopes survived. We had OAO-1 and OAO-B. Please don't ask me why this is randomly OAO-B. I'm not NASA. They named it. I just took this information from Wikipedia. So OAO-1 and OAO-B failed. OAO-2 is mainly a UV telescope, and OAO-3 was a joint effort between UK and US research teams and provided a lot of good X-ray data. Remember what I said about the atmosphere being opaque to ultraviolet? It's also opaque to X-rays and gamma rays, which is good for us because X-rays and gamma rays cause cancer. So does ultraviolet. It is not as opaque to ultraviolet. In fact, something like 200 to 300 nanometers is still ultraviolet. It's on the border of being violet light, but it's energetic enough that excess exposure to that can still cause cancers, is why you shouldn't, which is why sunblock exists, right? Okay, so I've mentioned some of these results. They obviously paved the way for future compared to then or current efforts. And there was a massive increase in the number of space telescopes, not just space probes. Space probes is when you throw something to the place. A space telescope is when you put it near you and you remotely observe something. So I'm not counting things like Pioneer, Voyager, Marina, so on and so forth. Those were equally as impressive, but we're just focusing on telescopes now. There was a massive increase, and we have a few of these. COBE, WMAP, CoRoT, Kepler. Everybody knows Kepler. Kepler is the uh, the pride and joy of exoplanetary scientists because Kepler alone managed to discover or detect about 4,200 exoplanets, which is about 91, 92% of all of the exoplanets we have today. And there is still data from Kepler that we haven't, sifted through. There's the Hipparcos, the Gaia space probes for astrometry. I'm not going to really detail all of these because you can, again, Wikipedia this. I don't want this to be any more of an info dump than it already is going to be. So if you're really, really interested about the nitty-gritty details, each of these, the Wikipedia articles for all of these are like, thousands of words long. So do read if you're interested. Yes, so very convenient QR code to scan for a list for a list of space telescopes up till now, and confirmed future efforts. So feel free to scan and save the tab for future reading. I'll just leave this here for like 5 seconds. 4, 3, 2. Anyone still scanning? All done? Okay. If you want to, I'll just come back to this slide in later. Right. So finally, we move on from those early efforts to the NASA great observatories, and they truly are great, right? There's a reason why they call them great observatories. There are 4 of them: Compton, Spitzer, Chandra, and Hubble. Each of these focused on one part of the electromagnetic spectrum. Everybody knows Hubble. Most people know Chandra and Spitzer. Not many people know about Compton. because Compton was a very short program compared to the other three. Okay, so let's move on. We start off with Compton, of course. It launched in the 90s, cost this much, and bit of information. So these were some interesting results. In particular, it discovered what we call soft gamma repeaters. It even discovered that the Earth emits gamma rays. Usually, it'll be like gamma rays have to be, require some very energetic processes. But no, these gamma ray sources were actually from thunderstorms, and thunderstorms are energetic. It's just that they're very contained. So some interesting observations. This is EGRET. Okay, I forgot what EGRET stands for. It's on my notes. Julian, can you read it out to me? Yes, energetic gamma ray experiment telescope. So this was basically a scan of the sky, and that line is the Milky Way. It's always the Milky Way. So whenever you see this ellipse and you see this big thing going across, you might see it when looking at an infrared image or a visible light image. This thing is always the Milky Way. So it's always there. And these are obviously gamma ray sources. So clearly, there's a lot of gamma ray sources near the center, which makes sense, right? Because the density of stars is nearer the center, the energies involved in collisions is much greater. There is also obviously a supermassive black hole. It's quiescent, thankfully, so we don't need to worry too much about us being fried by gamma rays from the black hole at the center. Okay, so now we move on to the Spitzer Space Telescope. It is an infrared space telescope. Again, some information. Anyone can tell me what this is? Anyone? Yes, this is the Andromeda Galaxy in infrared, taken by the Spitzer Space Telescope. So I didn't want to just put an image of the Spitzer Space Telescope because it's just a box. So I thought it would be more interesting to put, images that Spitzer captured. It was a helium cooled space telescope. I'll explain why you need helium cooling when we get to James Webb, because James Webb is the star of is everyone's next pride and joy. It launched in 2003 into a heliocentric orbit and was decommissioned not too long ago in 2020. The Spitzer was still operating fairly recently, and it was a fairly low resolution telescope. So one question might be, if it's so low resolution, how do we capture this big image? So what telescopes generally do is they point at one part of the sky that's at, at one part of the sky at a time, capture the data, then point to the next part, like right next to it, capture all that data, and so on and so forth. It's a bit like a CRT screen if you've seen one in slow motion. It's like kind of goes like this, you know, from top left to bottom right, slowly. And you might be wondering, hey, doesn't actually that wouldn't Andromeda move? No, no, not significantly. So it's not like trying to observe. Uh, let's see. It's not like trying to observe the moon, right? The moon moves pretty fast relative to the Earth, so you actually have to turn your telescope pretty frequently. For this, not so much. You can just keep it pointed at one point in the sky. By virtue of the fact that it's so far from us, it's going to roughly stay in the same spot, so no issues. And it enabled views into our universe like never before. Whoa, go back. Enable views into our universe like never before. There are many nice comparisons of uh, Spitzer observing through infrared. I unfortunately didn't have the time to insert this, but I strongly urge you guys to go Google some Spitzer results. There are some very beautiful comparisons of visible light being occluded. Sorry, dust clouds occluding visible light, whereas an image by Spitzer in infrared shows that the dust clouds are actually transparent to infrared, which is why, again, we want infrared. And I'll give you more reasons as to why infrared in a short while. Now we move on to Chandra, which is named after Subramanian Chandrasekhar. Anyone knows who he is? Did someone raise their hand? Yes, who is Subramanian Chandrasekhar? Yes, he discovered the Chandrasekhar limit. What is the Chandrasekhar limit? It's 1.44 times the mass of the sun, which is how massive a white dwarf can get before type 1a supernova, if I recall correctly. Right. So he's famous for that. He's also famous for a lot of other things. He had a very illustrious science career. Now, again, urge you to look him up. It was launched in 1999. It's still observing, and it's generally for deep space, high energy stuff. So, Julian, if you don't mind, can you help me pause the? I think there's a pause, but there's a way to pause the GIF. Oops. Like, go to the bottom right of the GIF. Sorry, the bottom left of the GIF. Okay, I could pause it on my slideshow. I don't know why. I'm so sorry. Never mind. Okay, so I'll just run through it. I'll just wait for it to come back at some point. This is why I shouldn't have used the GIF. Okay, so this is a composite, right? The one you just saw right now, the very colorful image. By the way, everybody knows, right? This is the Crab Nebula, right? Very famous, pretty easy to observe. It's near the celestial equator, so should be easy to observe. So that image was composite, and it cycles through infrared. Oh my God. Okay, I lost track. Okay, let me try again. Okay, radio, infrared, visible, ultraviolet, and X-ray. So notice in X-ray, you see these swirls, which are completely not visible in any of the other wavelengths. So there's clearly something extremely high energy going on in the depths of the Crab Nebula, right? You can't see it in any of the other images, right? You can only see it in X-ray. And obviously, the reason why you can see it in the composite is because it's a composite of all the other images. So this is one of the first discoveries that Chandra made. There's again a gigantic list of all the discoveries of Chandra on the Wikipedia page. Just Google this and you should be able to find out. And this is one image of a supernova in the Large Magellanic Cloud, a supernova remnant in the Large Magellanic Cloud taken in X-ray. So shortly after the supernova happened. So again, clearly a lot of high energy stuff. And science, and these again, this is not true color, by the way. This is just data captured by the sensors, X-ray data captured by the sensors, and then produced or modified or transmuted to a color that we can see or that makes sense to our eyes, because we can only see in a very limited range of 350 to 700 nanometers, plus minus. Right? We can't see X-rays. The Spitfire Space Telescope can. So we have to find some way to present it to us in an understandable manner. Okay. And finally, we come to the star of the show, or the sub-star of the show, the Hubble Space Telescope, also known as the wallpaper generator. Not kidding, not kidding. My desktop wallpaper is a Hubble Space Telescope image. If you guys are interested, I actually have prepared QR codes to scan to download Hubble Images. If you want to up your wallpaper game, I strongly urge you to scan these QR codes to find images that you like. Right? There are some really, really beautiful images available on both of these websites. So again, I'll give you a few seconds to scan. So what I do for like in my free time sometimes is I've really nothing better to do. I'm bored of games, I'm bored of reading. So I go to, especially the ESA Hubble website, I go to picture of the week and I just scroll through and I spend like 5 minutes just oohing and eyeing at images. Okay. If you're interested, my desktop wallpaper is POTW 1929. I can show it to you later. Okay, everyone finished scanning? Anyone still wants to scan? No? Yes? Okay, great. Okay, who knows about the Hubble mirror problem? Raise your hands. Who has heard of the Hubble mirror problem? Anyone else? No one? Okay. So I was going to say the problem with the mirror, everyone knows this, but clearly not. The Hubble Space Telescope. Okay, this kind of harkens back to what I was saying earlier on about grinding massive mirrors correctly. The Hubble Space Telescope's primary mirror was ground incorrectly. So this This is M100, Messier 100. It's called the Whirlpool. No, it's not the Whirlpool. It's called the Pinwheel Galaxy. Yes, so this is called the Pinwheel Galaxy. This was the image first taken by the Hubble Space Telescope in 1990, immediately after launch, and it was widely there was a huge uproar about NASA, you spend so much money, but you screwed this up. You can't even grind a telescope mirror correctly. But in actual fact, the discrepancy, I think, okay, I don't want to be wrong about this, but it was on the order of micrometers. Yes, Suchan? You- The discrepancy was smaller than nanometers. Yes, thank you. So that's nanometers. So that's like, uh, smaller than most human cells. So the discrepancy was that small, and yet it resulted in such a poor picture. So this is how strict the tolerances are for mirror grinding. And they ground the mirror wrongly. Who ground the mirror wrongly? Uh, you can Google it, but I think it was one of the NASA contractors who screwed it up. And the reason was because this was the test setup, and when they tested it wrongly, and therefore the grinding was incorrect. So everybody widely ridiculed NASA. They had to send up a mission just to correct this. And what happened was they actually put spectacles, in a sense, on Hubble. So they were like, okay, we can't fix the mirror. The mirror weighs, uh, you'll see how much it weighs in a while. It weighs a lot. We can't, chuck it out. Can't bring it back. We can't, launch it. It's a waste of energy. It's a waste of rocket fuel. So what they did was they just put in a new instrument package which corrected for the aberration by itself, and therefore this is the new image. So this was WFPC1, the Wide Field Planetary Camera, Wide Field and Planetary Camera 1. This was Wide Field and Planetary Camera 2 which was installed in 1994. So they had to go 4 years with this kind of imagery. Admittedly, it was one of NASA's low points, very low points, because by then all of the excitement of the late 1960s, all the Cold War energy had dried up, and they were like, NASA's a waste of money. So a lot of politics going on, and it was quite miraculous that they did manage to fix this. And modern Hubble images look really, really good, as you can see in on your phone, right? So Hubble is very interesting. It is huge. Okay, it's about as big as a public bus. So imagine the shuttle bus. That's about how big Hubble is. It's a cylinder. It's not a square. And it's about 2.5 meters wide. The mirror itself is about okay, not 2.5. I think more closer to 3. The mirror is about 2.5, 2.4 meters wide. So 1 meter is about I'm 1.7, so it's about here. It's about maybe another half of me. So that's a big mirror. Uh, it is 818 kilograms. Yes, so it's very heavy. The replacement package that they sent up, WFPC, was I think something like a quarter to a fifth of the weight. And weight savings are very, very important in rocketry. There's not a rocketry discussion, so I'm not going to go into that. And it's so good that the best terrestrial telescopes we have today, I'm talking about the best, including the biggest, like the Very Large Telescope. You saw how big it is. Some of the newer ones, like the extremely large, no, not the extremely large telescope, the Subaru Space Telescope, are much, much bigger than Hubble, but they have roughly the same resolution as Hubble because of the atmosphere. And the best thing is that most of these telescopes are built high up in remote locations. They are like 4.5, 5 kilometers above sea level, and they're still not as good as Hubble, which only, in comparison, only has a 2.5 meter wide mirror. This wide is diameter, by the way. Sorry, 2.4. Hubble it's difficult to understate the influence of Hubble on modern day astrophysics. Hubble is so important to us that we're actually sending up a replacement again. We'll see that in a short while before we want to, decommission Hubble. It fine-tuned the age of the universe. Before Hubble, people were actually not sure about the age of the universe. There was like a one order of magnitude. Okay, sorry, one order of magnitude in the sense that 10 billion to 20 billion. So that's twice. That's one order of magnitude. So that was the error in the assumed age of the universe. This was fine-tuned only after Hubble observations to the current value of about 13.7, which is pretty good, right? It also managed to observe the Shoemaker-Levy 9 impact on Jupiter, which was pretty good. This was even despite, this was in 1994. I think, I'm not sure if it was before or after the replacement, but it did. And this also brought a lot of improvements to impact science, to asteroid science, which is good for us. And the Hubble deep fields and the ultra deep fields have, okay, this is for phrasing, have revolutionized the understanding of the larger structure of the universe. So what one scientist did was, okay, it was not a scientist, it was actually the guy in charge of allocating time on Hubble. He gets some time to himself, he or she or they get some time to themselves to do whatever they want with, to point the scope at wherever they want. So what they a request they got was, just point it at some random area of the sky continuously, every time you get a chance, and see what you get. Like, it was totally random. And what they discovered was in an area that's about something like a few arc seconds big, so it's something like 1/100th to 1/1000th the size of the moon that you see. They discovered 10,000 galaxies in that single image. So it's like this tiny area up there in the sky, zoomed in, and there are 10,000 galaxies there. We just can't see them, they're just so far away. So Hubble just pointed at that location for about a few months to collect as much light as possible. Again, I don't have that image here. Apologize for that, because it is a very impressive image. You can Google it. So this, I do have this though. This is the Mystic Mountains. This is nebulosity in the Great Nebula of in the Great Carina Nebula, or the Great Nebula in Carina. It is one of the biggest nebula. The Carina Nebula is one of the biggest nebulas uh, in the night sky. We cannot see it in Singapore because we can't see anything in Singapore except clouds and sometimes planets and the moon, and sometimes the brightest star. So that means we can see something, but never mind. We can't see this. We have to go to some really dark places, and it is actually very impressive when you can see it because it's huge. And this these are actually dust clouds, right? This is actually areas of active star formation. There's actually a lot of really interesting things you can see here. You can see this comet-like formation over here. You can see this, this ejection. So there's one star forming over here. There's more star formation over here. This is generally like a stellar nursery. It's something like the Orion Nebula. The Orion Nebula, obviously, Hubble has pointed at the Orion Nebula. Also very impressive, right? In fact, Hubble has pointed to many details within the Orion Nebula, like the Horsehead, the Flame nebulae. Anything else? Is the Eagle Nebula within the Orion Nebula? I can't recall. Many very interesting images. So really wallpaper. I would use this as a wallpaper, right? Okay, moving on from Hubble, I did mention I would briefly touch on some other efforts. I'm a bit tired of talking about exoplanets because I've given a lot of talks about exoplanets. So I'm going to talk about something different today, the cosmic microwave background. Uh, there are actually three space probes to um, explain and to examine this CMB. What is the CMB? So about 300,000 years after the Big Bang, the universe became transparent. Up till then, it was opaque. Why was it opaque? Because the universe was consisted of a plasma, and plasmas are opaque to light in general, especially visible light, right? And so plasmas absorb photons, and they just get more, and the particles just get more energetic. So they just light goes nowhere. At some point, all of these electrons and protons and everything just combined into atoms, and suddenly the universe was transparent. The light emitted then, that was about 13.4 billion years ago, is what we see here. right? It's everywhere. It's all around us. So there's a very, very, very faint amount of microwaves arriving at Earth from everywhere at once. The universe itself is emitting that microwave radiation. So why is it microwave? This is because of a phenomenon called redshifting. So the longer back, it's a complicated theory. I'm not going to go explain Doppler theory and everything. So in summary, the longer back some light was emitted, the longer the wavelength it becomes. This, regardless of the initial wavelength it was initially emitted. So the light that was initially emitted was probably something like visible or ultraviolet, right? This has been redshifted from about 500 to 700 nanometers to something like, what is the microwave? I can't do the calculation off the top of my head, but a few tens of micrometers. That's why it's called microwave, right? Yeah. Duh. So a few tens of micrometers, and this wavelength has increased, right? That's called redshifting. It happens regardless of the source, right? So let's move on. Okay, wait, no, not moving on, right? So COBE, okay, stands for Cosmic Microwave Background Explorer. I don't know why they didn't call it COMB, which would have been a bit cooler, but this was the resolution of COBE, right? It's just one big blur. This was in the late 1980s. This was WMAP, Wide Field or Wilkinson Microwave something something. Yes. I don't know what I can't recall off the top of my head what the AMP are. I don't think I noted it down right. Yeah. And this is the Planck Observatory. These two are NASA observatories. The Planck Observatory is an ESA effort. So obviously the Planck Observatory drastically increased the resolution of the microwave background. You might ask, why do we want to increase the resolution of the microwave background? We already know that it's there. Well, small fluctuations like these in the microwave background give evidence that there were small fluctuations in the overall makeup of the universe, which is what led to, things clumping together and galaxies actually forming versus the universe being, one homogeneous soup of gas and dust. Right? If the universe was homogeneous, there would have been nothing happening. It would have been very boring. We wouldn't exist. Nothing would have happened. But there were very minute fluctuations in the densities, and this, although it may not necessarily tell us why, it tells us where and by how much, which is still useful. Okay, so now we move to the James-Webb Space Telescope, right? I'm just going to call it Webb from now on because it's one syllable versus JWST or James-Webb Space Telescope. Why is it such a big deal, right? Everyone knows that this was launched last Christmas, right? Or is anyone still operating under the view that it has not launched and will never launch? That was the meme until, yeah, sorry. Let's not go there. Let's not go there. But yes, okay, that was the meme. I also wanted to put an XKCD here, but this was a bit last minute. Never mind. So yes, that was the meme, right? It was never. It was just delayed and delayed and delayed until finally it launched, which is a very good thing. It launched perfectly. The rocket that it launched on performed admirably. Uh, the deployment was perfect, and right now it's pretty much just setting up. So that's good. Okay, so I'm gonna lace you with some specs and cool facts. Again, Webb is optimized for infrared. That's like the 10th time I'm saying infrared now, right? There's one particular instrument on James Webb which pretty much is the flagship instrument of James Webb of Webb. It's called MIRI, Mid Infrared Imager, MIRI. It's cooled to about 6 Kelvin, which is very, very cold, with a closed loop helium pump. This is similar technology to Spitzer, except that Spitzer eventually ran out of helium. And that was not the only reason why it was decommissioned. It also got too far away because it was placed in a heliocentric orbit. So it was not within the gravitational influence of Earth. Now that this helium pump is closed loop, it behaves a bit like your refrigerator at home. So your refrigerator doesn't really lose coolant, right? If it does, it means your refrigerator has a problem. Please go and fix it. But what this essentially means is that it can basically cycle the helium over and over and over, right, using power and using electricity, of course, a little bit of thermodynamics, and keep one side really cool, really, really, really not cool. Cool is understated. Really cold, really damn freezing cold, and keep the other side moderately warm. Like by moderately, I mean like 55, 60 degrees Celsius. The key thing is the difference in temperature rather than the absolute temperatures themselves, right? And it has a massive sunshade. So again, I don't have an image of Webb. I don't think I need an image of Webb. I think everybody has seen it. It dominated the news cycle last Christmas. So if you don't know that it launched, or if you don't know how it looks like, you probably have been living under a rock, right? And there was a very complicated, okay, I wouldn't say deployment, but complicated arrangement, right? So that it fits inside the Ariane 5 rocket. Ariane 5 already has a pretty big diameter. It's one of the wider rockets we have right now. And it had to fold up in very complicated ways. There are videos for this. You can just go to YouTube and search James-Webb deployment. And there's a very beautiful animation about how it folded. It literally unfolded like a flower. I can't put it any better than that. The engineers who worked on James-Webb are insanely smart. So life goals, right? Okay, and it was tested repeatedly to avoid the Hubble Space Telescope mirror scare. And while it was being tested, there were many, many issues that cropped up. One big issue was when they tried to unfold the sunshade tall. And that delayed the launch by a year and a half by itself because they had to buy a new sunshade. They had to buy a new sunshade. They had to find ways around the whole tearing issue. Now we move to why infrared. Finally, you'll be like, okay, this guy's just been boring us about infrared. Why infrared? Two big reasons. Start off with exoplanetology. So exoplanets are very dim, right? They don't give off any light of their own. Their parent stars, on the other hand, are bright, are big, and are hot. So it's like trying to find a firefly or a candle light next to a stadium lamp. You can't do that. Actually, that's a bad analogy. It's like trying to find a tiny pebble, next to a stadium lamp. All you have is the light reflected off that pebble to find it, right? And you need extremely sensitive optics to detect this kind of dimness. So, and gas absorption happens in the infrared, right? I'm not talking about Kepler, all of these transit detection telescopes. They operate in the optical region, which is the visible, most of the time, because all they need to do is detect a small dip in the brightness of the star. They don't need to actually characterize the wavelengths, characterize the light that's coming in, right? All they need to do is just detect a very small, and these differences. I'm not gonna understate it anyway. It's also very small, right? So they have to be sensitive in their own right, but it's not the same as infrared. And what do I mean by gas absorption happens in the infrared? So do you remember the complicated chart I started off with? Right? You see all of those absorption, you see all of those dips in absorption or transmittance. This is where gases that are important to us, water, oxygen, methane, methane, carbon dioxide, ammonia, right? These gases absorb light at certain frequencies, at certain wavelengths. Same thing. And these wavelengths are almost always in the infrared, at least for the temperatures that we are concerned about, right? So this allows for atmosphere characterization with spectrography. What happens is you basically basically the planet passes in front of the parent star. This light from the parent star goes through the planet's atmosphere. The gases in the planet's atmosphere absorb some of this, and when you put that light through a prism, right, you'll see the spectrum, and there are black lines. So those black lines correspond to certain gases. And in this case, right, I've mentioned some of the gases that we're interested in. Okay, so not just exoplanetology, right? We're also interested in cosmology. Okay, before I move on to cosmology, I also want to talk a little bit more about exoplanetology. Newly forming planets, like characterizing the formation and evolution of solar systems or star systems in general, is also a case for working in infrared, because many young star systems are completely covered, are blanketed in dust. I mentioned earlier on that dust clouds absorb strongly in the visible and higher wavelengths, but do not absorb infrared much. Why infrared in particular? There are many reasons for this, but they just don't absorb infrared that much. So using an infrared telescope means we can see through those dust clouds, right? We can see through anything that's blocking, and we can actually understand the overall structure of newly forming star systems, as well as the larger universe. So remember that whole Mystic Mountain nice image I showed. If you used an infrared camera, that would just be like this, it would just be transparent. You'd see the stars behind what's there, right? So now we move on to cosmology. I've mentioned that most deep space observation has been dramatically redshifted. These distances involve something like on the order of 10 billion light years. So a billion light years is a lot. It's about 1,000 times the distance from us to the Andromeda galaxy. And a million light years is about 1,000 times the distance from us to most of the stars around us, right? So it's a lot. And like I've mentioned this, right? These block visible ultraviolet, X, and gamma. I just mentioned this, and they're transparent infrared. Okay, which is why we emphasize infrared astronomy so much nowadays. Which is why there's such a big deal about James Webb, because it allows us to see the universe in ways we haven't really been able to see so far. And I didn't mention some things about, how it's at L2, so far away from the Earth, but these are all also relevant to the entire mission profile of James Webb, right? That's also why it has a massive sunshade, right? Did I include that slide, or did it go away? Oh God, I think I reordered the slide. Right. So there's this mass. Oh, sorry, my bad. I'm so sorry. Yes, so this massive sunshade. Why is that? Why do we have that sunshade? We want to block out the infrared light emitted by the sun. Why is it at L2? We want to avoid the infrared light that is both emitted and reflected by the Earth itself, because the Earth is not, again, not at 0 Kelvin. It has a non-zero temperature, so it too emits in the infrared. You might ask, how come, you just said the Earth's atmosphere, is excuse me, opaque to infrared. The Earth emits infrared. How do infrared thermal sensors work? Have you guys seen those, infrared cameras where you point at like something really hot and it looks purple or it looks yellow, and then you point at people and then people's faces look weird, and then you point down, you can see everything even though they're wearing clothes, right? The reason is because they are a lot less sensitive, right? All they need to do is detect a very small range of temperatures in a fixed range of temperatures, right? And even your normal camera sensor can do that. So if you ever want to detect some infrared, take your TV remote, take your phone camera, try to press a button on your TV remote, and look at the front of your TV remote through your phone camera. You might see blinking. Even more interesting, for those of you who have new iPhones with Face ID, try to look, try to take a photo of yourself when the iPhone is scanning you for Face ID. You will actually see the infrared pattern on your face, right? This is invisible to the human eye, but very easily visible to normal cameras. It's actually pretty cool, right? So yes, this is why we have infrared. And not only do we have the James Webb Space Telescope, we have the Nancy Grace Roman Space Telescope, which is slated to launch in May 2027. Uh, it's supposedly a maximum cost of US $4 billion. I put the laugh emoji there because James Webb was supposed to launch in 2007, and it had a maximum cost of 1 billion, but it actually costs 10 billion now. So, And this is and again, this is essentially the science profile of NGRST, also called W first, Wide Field Infrared Space Telescope. I don't know I think it stands for wide field. NASA calls it NGRST. I think it's a missed opportunity to call it engrossed, NGROST. This is an image. This is a rendering of the space telescope. It has not been built yet. It just left critical design review last September. It's one of the very new things. Okay, I'm willing to bet that it's not going to launch earlier than 2030. Right. So anyone who wants to take me up on that, I don't mind. I'm willing to bet it will launch into the 30s. One interesting thing here is that it was actually one of two telescopes donated by the National Reconnaissance Office, which is a US agency, NASA. The National Reconnaissance Office is essentially US's spy agency, satellite-based spy agency. So what they are telling us but not telling us is that they have two Hubble level satellites, or more than Hubble level satellites pointed at Earth, just spying on Earth, right? So imagine if you take something as powerful as the Hubble Space Telescope and point it at Earth. The estimated analysts estimate that the the official resolving power of most US telescopes is about 10 centimeters to 1 meter per pixel. So if you zoom in on Google Maps, right, at some point you'll see the pixels because the satellite has to take photos of the Earth. It is suggested that the US has intelligence and has images with quality exceeding 1 pixel, 1 centimeter per pixel. So imagine you have a satellite up in space that can take, you can pretty much make out individual people on the street, right? And it's not just a black spot, it's you can make out what color of t-shirt they're wearing. That kind of spy thing, which is pretty cool, but also very creepy at the same time. Yeah, another thing is that they are essentially the same size as Hubble. So they were built based off similar plans. So the mirror diameter is exactly the same. It's just that the how the spacecraft is built is obviously going to be different because it's optimized for a different mission profile. Right. So I'm gonna end with the Decadal Survey 2020, and the results were just released last November. There were two basic, the Decadal Survey 2020 is a survey conducted by the U.S. government. You might be like, Sharad, why are you focusing so much on the US? Because unfortunately, most of the space telescopes, most of the interesting space telescopes launched into space are American. The Soviets were very, very secretive about what they launched anyway. I did discuss a few European space telescopes. Incidentally, CHEOPS is a European space telescope. I think I briefly mentioned it, listed it on a slide a while ago. So there are two results or two recommendations from this survey. We have deep space observations, which means more observations of black holes, neutron stars, evolutions of galaxies. So basically, big, energetic, massive things that are very far away, as well as very small uh, things that are a lot nearer to us. So exoplanets attempt direct imaging of exoplanets. We want more detailed atmospheric characterization. So imagine you could detect what's in Earth's atmosphere from about 10 to 50 light years away. That's the kind of imaging precision and power that they are looking at. And these are four suggestions that have evolved, that have erupted, or that have come up uh, after the Decadal Survey. I'm going to talk about LUVOIR because it has a very cool name. HABEX stands for Habitable Exoplanet Origins. It wants to detect the origins of life as well as the origins of the universe. And LYNX is the odd one out here. So all of these are infrared in some manner. LYNX is the odd one out. It's the only X-ray space telescope. So clearly, the guys who are focusing on LYNX don't care about exoplanets. I mean, sure, you do you. So in particular, I'm going to focus on LUVOIR. LUVOIR is huge, or at least the plans for the idea of LUVOIR is huge. It's a completely next generation telescope. It stands for Large Ultraviolet Optical and IR. Large is an understatement, right? It's equal to putting the Very Large Telescope in space because the mirror is huge, has a 15-meter primary mirror, and we can effectively take photos of Jupiter or Saturn or Uranus or Neptune without ever going to those places anymore. So those telescopes are just so crazy huge that that you wouldn't need to send a space probe there unless you actually wanted to sample the atmosphere or something. Right? And this also allows direct imaging. This is one of the goals actually of LUVOIR and the Decadal Survey 2020. You want to directly image an Earth-sized exoplanet. So imagine a space telescope operated by some alien civilization 50 to 100 light years away, pointing their own LUVOIR at the solar system, not realizing that that there exists an Earth, and taking a photo of Earth. So that's mind blowing, right? There are many scale examples. So it's like taking a photo of a candle on the moon from Earth, something like that, right? And it is huge, right? They are very, very big, right? There are two plans for LUVOIR. There's LUVOIR B, which is about 8 meters, and there's LUVOIR A, which is the big boy, and it has a 15-meter mirror diameter. Again, you notice that these are hexagonal mirrors. The original plans for LUVOIR was to be a circular mirror, but then they were like, you know what? Except hexagons are the bestigons. So they just did this. And that is the Hubble Space Telescope and W first. So I mentioned that they are the same mirror, right? So that's that in comparison. They will fit in the Space Launch System and the Starship, neither of which have launched yet, by the way, after folding. So yeah, this I think that should be it, right? That is a very long summary of space telescopes. Any questions? Um, Theoretically, yes, but that's the that's one of the engineering goals of space telescopes is to make them as self-sufficient as possible. For example, James-Webb is designed to operate up to 20 years, right? The actual mission profile, the official mission profile is 10 years. But engineers, again, are especially NASA engineers are very good. They tend to over-engineer stuff. So all of these failures and consumables are built in. The calculations of these consumables are built in to provide a mission lifetime. At some point, you'll have to, um, how do I put it? You'll have to, end of life some of these things because you have better technology, right? For instance, you wouldn't launch Sputnik anymore, right? You have better technology now. So there's a balance between maintenance and technology. Uh, Hubble was designed to be maintained. That's why it's in low Earth orbit. It was maintained. Like I mentioned, the whole mirror swapping thing was shuttle. I think I can't remember which shuttle mission. There was a shuttle mission. They brought they brought the telescope in. They unscrewed stuff. They spannered stuff to maintain it. James Webb is supposedly designed to be maintained, but it's very, very far away from Earth. So now it's kind of up in the air. As for these, as for the newer telescopes, they are just plans on paper now. So who knows? Many other space telescopes were maintained as well. Many weren't. Many were just, after 10 years, something spoiled or something stopped working. So they either find ways around this. One big example was Kepler. So Kepler had 4 reaction wheels to turn the telescope and point at different things. 2 of the reaction wheels failed, so that means it could not perform its mission. They had to revive Kepler in a different. They had to use solar pressure. There's a very nice infographic. I have it. I have it in one of these slides somewhere, where they use solar pressure from the sun to position Kepler, to point Kepler at different things, and they actually repurposed Kepler from a purely exoplanet detecting mission to something else as well. So there are many alternatives you can have to sending people up there to maintain things. It's actually one reason why we want space telescopes, because like I said, on Earth things get dirty. Things can break. In space, there's nothing to break something. So once it's there, it's there. It depends. For instance, Spitzer is still in space. It's small enough that it's not probably not going to affect anything. Again, we have very good tracking, so we know where everything. We know pretty much where everything is. Space telescopes nearer the Earth will deorbit as they experience atmospheric drag, especially those in low Earth orbit. Under geocentric orbit, they usually send them up to a graveyard orbit, or they deorbit them. The usual idea is to just push them to a graveyard orbit, so they orbit a bit higher than geocentric, so that it frees up space for satellites to be there. Any other question? Any questions from this side? You wanted to ask something, right? Okay. Any more questions? About going once? Yes, Julian? Yes, actually. In fact, the one big area of research right now is actually gravitational waves, right? If I recall correctly, LISA is such a constellation of space telescopes, which uses some kind of interferometry technique to detect gravitational waves from merging black holes. So these kind of high energy events typically give off gravitational waves, right? If you have black holes merging or neutron stars merging, or something along those lines of very massive, very compact object moving very rapidly through space, they emit gravitational waves. And to detect them, what you basically do is you put a few things some distance apart, and you know that distance. And as the gravitational wave passes you, that distance changes a little bit, and you detect that difference in that distance, and you say, okay, this is, and you characterize it a little bit, and you say, okay, this is my frequency, this is the wavelength of the gravitational wave. So all waves have a frequency, have a velocity, and so on and so forth. So yes, definitely possible. Definitely yes. So this is just one example. I had a very crazy idea of instead of launching Louvois as one unit, why not just make, instead of hexagonal segments, use triangular segments and make all of the segments into tetrahedrons. Just dump them into a rocket, just launch them up, and use reaction control to arrange everything nicely into a mirror. Then I realized I don't work at NASA, so the idea is probably gonna, right. So, any more questions? If not, I have a few questions for you. Julian, can you help me move to Kahoot? Yes, sorry. Last question. Okay. This is, how do I put it? The larger the mirror, the better your collecting power. So these mirrors are curved this way, curved concave, right? And there is, okay, forgive me, I'm just going to turn up the lights so that presentation's ended, so I'm just going to turn up the lights, right? The mirrors are curved this way, concave, right? There is a secondary mirror over here, right, which is also concave, convex, right? So what happens is light comes in this way around the secondary mirror, bounces off this concave mirror, goes inwards into the secondary mirror, all right, which then bounces off that light again inwards into a little hole on this primary mirror, And inside all of this is where all the sensors and where all the detection is, right? So the bigger the mirror, the more light you can collect, right? The bigger the mirror, longer your focal length. So the deeper you can zoom in. And the bigger the mirror, the less time you have to spend on any one object. The more improved your resolution is, right? There is a formula that I entered very early on. It is a function of how big your mirror is, which is in turn a function which is in turn affects how long your focal length is. And yeah. Okay, so that's all for the questions I have. Please join this Kahoot. I hope I've set up all the questions correctly. And have a great night. Okay, so yes, when talking about the reason that this works against the spirit of the question, right? You would not want to send a space telescope. Sorry, thank you. Okay. You would not want to send a space telescope away from us because it's so far away, and it's like the question he asked, they're difficult to maintain. Yes, but it's not a reason why we need space telescopes. I'm asking about reasons why we do need space telescopes, and well, yes, yeah, there we go. I hope that's clear. Okay, next question. No, just no. Yeah, yeah. Okay, technically yes, but okay. I understand that I should have clarified the question. As a black body, it doesn't. Right. Right. These emit visible light, but these are not the Earth. I'm talking about the Pretty much, actually. You underestimate how bright city lights are. Sorry, you overestimate how bright city lights are. But yes, the question was in the spirit of black body radiation. Well, yes, hexagons are the bestagons. Yes, right. I think I spent too long discussing this because when you have a grid of hexagons, it's just a flat thing compared to a big solid block of glass, right? And you can actually, and one new uh invention I neglected to mention in the lecture is actually adaptive optics. So what adaptive optics does is actually manipulate the the surface of one single segment, right, by sending waves across, by sending tiny acoustic waves across the surface of each segment. So this is some really crazy technology that has been invented, right? Okay, so that's 3 questions down. Next question. Hey, how come got no podium? How come got no podium? Like, oh, okay, the only come. Okay, no. I mentioned that Hubble did not need a new mirror. It All of the new instruments that have been installed on Hubble. So Hubble, okay, another thing is that there are actually slots inside the telescope to install new instruments. They left a few empty, right? One was sacrificed to fix these aberrations. So every single instrument itself contains a fix for the aberration now. The mirror is still technically problematic. It's still not up to spec. But it's like I said, it's like wearing spectacles, right? Each instrument has its own corrective optics. That's the word for it to fix the aberration. All right. Okay. Okay. Contentious answer, but you actually. Oh my god. Okay. Um. I understand the contention. Okay. Uh. Maybe I should have. Okay. You know what? Hmm. Can we avoid this question? Okay, never mind. Forget it. Okay. The spirit of the question was to, you know, hope you guys understand that black holes in general are high energy stuff. The sun, you do need you do need okay, we do observe the sun in infrared. Okay. The thing is that yes, okay, we don't need sensitive infrared. Right. My bad. Right. Okay. Yes. Let's just pretend this question does not exist. Okay. Oh God. Okay. So the answer is false. I mentioned SLS and Starship. There's again some contention, but in my view, Starship isn't an existing rocket in the sense that it hasn't been assembled, hasn't been tested as a complete setup, right? Compared to Ariane 5, for instance, or Delta 4, right? Those are existing setups, or Falcon 9, right? So that's what I mean by existing. It has been tested, but it is not. It is not. It's like saying, can you guys fly in the Boeing 777-8? No, it exists, but you can't fly as a paying passenger. It's still being tested. It's the kinks are being ironed out. There we go. Okay. Okay, no prizes today. Sorry? Yeah, sure. Okay, so whoever's graveyard orbit, please come collect your. Okay, please take note, right? Okay, and there are also goodie bags. This is not relevant to the prizes here, by the way. We will take note of your performance, and hopefully in the future, give you some prizes. All right. I hope you guys enjoyed the presentation and the quiz. Okay, so if the winner wants, you can take an extra goodie bag. Okay, right. Have fun. Have a great night. Bye bye.
Everyone. That's not the end of Sarah's presentation. If you have any questions, you can direct or ask me. But yeah, hope you enjoyed the presentation and hope that you learned something. Now we'll invite Lightman up. Unfortunately, it's raining now, so we can't set up a telescope directly because my cause the optics become low. So Lightman has prepared a different activity for you all. Lightman, please. Alright, let's go. Okay. Okay, never mind, it's fine. Hi everybody. So I'm the Lightman. I'm actually not from NUS. I've been hired by NUSAS to do this activity. So I'm actually an external vendor. I'm not from NUS. So what we're gonna do is, because the sky looks very gloomy, right? So we can't really do a lot of star seeing. So instead of taking picture of stars, we'll be taking picture of each other. Okay, we'll be doing this activity called light painting. Do you all know what is light painting? Okay, actually, computer man, can you do you have internet? Do you have access to internet? Okay, can you go Google and search light painting? Yeah. So yeah, let's go to images. Yeah, so we'll be doing something like this. Yeah. Yeah, um so all you need is a camera. How this works is we set the shutter speed of the camera to super low. Not be super long, correct, super long. So what happens is, as you're moving the light source around, right, the camera will be taking in the light and then saving it as one picture. So that's the science behind it. So we'll be doing it here. We need a dark room. I have these little mini lights, okay. It's just nice to capture the picture. What? Oh yeah, nice. You can use that. yeah, too bright and it would just blur. You would just overwhelm the camera with light. Too faint wouldn't really make the picture as defined as this, right? So this is white light, but I have some cellophane paper and rubber band. So you take the cellophane paper and you wrap it around the light source with the rubber band. Yeah, so we have red, blue, and white. Of course, I forgot to bring yellow, but that's fine. You can make purple as well. So yeah, really the limitation is your creativity. You can decide how you wanna take pictures. Is so you can use it as like your tele DP or like Instagram or what. Like you can even spell out NUSAS or something. Or you can do an outline of your body, or you can do like interesting pictures. I wanted to do this, but OSA said no, because that one you need like sparklers. But yeah. So yeah, we can yeah, okay, let's go. We can do this, right? Yeah, we can do this. Okay, cool. Nice chat. So we'll just be offering the front light.
I think you need to turn the thing. Push the top. Push again. Push it. Nice.
Okay.
And off to the projector.
Yeah. Light man. Yes. Oh. Okay, so wait. Your camera. Yep. It's up here.